Let me introduce myself. I'm Daniel Ho here from the College of Science, Associate Dean for the College of Science. Today I'm really honored to give the introduction to our speaker today. Let me make a start. Perhaps there's a few words later on difficult for me to pronounce. Excuse me for that. Okay. Let me introduce our Professor Benoît Perthame. Am I right?
Yeah, absolutely. Very nice.
Okay.
Yeah.
Okay. Now, Professor Perthame is a professor of mathematician. Is a mathematics at the Sorbonne University in Paris. And personally, at the moment, he's the director of the laboratory of Jacques-Louis lines. Before, he has been a professor in Echo Lomini Supini, and also the founder of a team called BAN, a team focused on mathematical modeling in life science at the National Research Institute on Informatics and also Automatic. Now that is we have an email the institute. Now, Professor Perthame, his research activity concerned with partial differential equation, the mathematical objects which serve to relate variation in space and time as they arise in fluid flows and heat transfer. And he has introduced a new striking relationship between the dilute fold and also dense fold. That is we call it mathematically is Boltzmann equation and Euler's equation. You will see it later. And recently, he has shown the important role played by nonlinear PDE in a number of problems, from biology, cell motion, and also cell colonies, cell organization, Darwinian evolution, modeling tumors growth, and also neural network. Now, Professor Perthame, he was really a plenary speaker of ICIAM in 2011 and also ICM in 2014. Now, most of all, he was elected at the French Academy of Science in 2017. Yes, I think I'm right. Okay, today we welcome our speaker today, and the topic is some equation of mathematical biologists. Next.
Okay. Okay, right. Okay, so thank you very much for this introduction and for the invitation to be in this nice place to visit again City University. It's a great honor for me to be with you today, and thank you for coming to this talk, which goal is to give a survey of mathematical equations written in terms of partial differential equations in biology. Okay, so this will be on. No, it doesn't work. Okay. So I think most of you know that many fields of physics are written in terms of partial differential equations. And these equations have famous names, mostly from the 19th century. And they represent fundamental principles of physics. And the question many people ask me is whether there are principles in biology and there are equations in biology like there are equations in physics. Some people say no. In any case, mathematics is not the good language for biology, and we should turn to more computer science objects. On the other hand, Alan Turing was saying that any science is a differential equation. So I would like to explain a little bit what I have in mind behind these ideas. So the first principle that I think everybody knows is the equations of Newton, the fundamental principles of dynamics, which is written in terms of the two equations for the velocity and the acceleration of a particle. I think everybody learned that in early mathematics, early physics. If you go further and you look at a big set of equations, then of particles, then you find a flow which is well described by the Euler equations, the Navier-Stokes equations, which I wrote here. If you consider now a dilute gas, so not the gas as in this room, where you have a dense gas which is well described by Navier-Stokes. If you consider a dilute gas, then you have another object which is called the Boltzmann equation, which describe how these balls which collide or interact will be described in another set. So in Navier-Stokes equation, you describe position, velocity, temperature in terms of their position and time. Here, it's a more elaborated object where you describe the density of particles not only by their position x, but also by their velocity psi. Okay, so you look at the number of particles, or the density number of particles, which at the position x have a velocity psi at the time t. And this object, of course, the first term is just a transport term, saying particles are moving velocity psi, and then all the binary collisions described here in a complicated way are in what is called the binary collision. So these are the Boltzmann equation. And of course, nowadays, we know quite well that the Euler equations, the Navier-Stokes equations, the macroscopic equations, which only depends on t and x, can be considered as a certain mathematical limit of the Boltzmann equation, when now you take the mean free path, the collision here very big. This is kappa tends to 0 in this term. So if these collisions are very numerous, you get Navier-Stokes. So the molecules in this room, there are many of them. At each place you can see there are many collisions. This is what it means. And if you are at this regime, you recover the Navier-Stokes equation. And we also know that if you take a system of particles described by the Newton equations with the correct forces, if you take the limit capital N number of particles tends to infinity, you will recover the Boltzmann equation, of course, scaling correctly the force. So we know perfectly well all the relations. Not only we know the principles of fluid mechanics, of dilute gases, of particle systems, but we know all the relations which explain how one of them is derived from the other one. Of course, there are many other equations which come from physics. The Laplace or Poisson equation are used for electric potentials. The oldest equation written by D'Alembert is the wave equation, which describes how a wave is propagating. The Fourier equation describe the dissipation of heat in a media. Maxwell equations describe electromagnetic fields. And if you go to quantum mechanics, you will find the Schrödinger equations, which are fundamental principles of quantum mechanics. But there are many other equations. So this is a list of some equations that mathematicians are studying. I know the list is not complete. If you have some other names, tell me. There are many equations describing all the physical situation you can imagine. And in biology, do you have ideas of names of equations which are famous in biology? So when I thought of this question, the first name which came to my mind are the Lotka-Volterra equations. I think this is the system of equations that is the most studied, or at least the most exemplified in, at school. So it describes how small fishes will interact with predators, saying that these small fishes that eat phytoplankton or plankton, and they grow with a certain rate. They are eaten by big fishes with a certain rate, B, and when they are eaten, they are coming back in the food for predators, which are growing according to this uptake. And predators would die if they don't have food, and the food for them is considered to be the small fishes. So this is an equation which is very famous because it has an Hamiltonian structure. Solutions are periodic, so you can do easily calculus around this equation. The name of Lotka Volterra nowadays doesn't only cover this particular system, which is your historical equation written at the beginning of the 20th century by both Lotka and Volterra independently. It's a generic name now for systems of equations which should describe more complicated situations, mostly coming from ecology. So typically, now, rather than two species, you would say that you have a number of species described by parameter x. X can be discrete or continuous. You will consider the number of individuals with a trait, with a phenotypical trait x at a time t. And usually you need environmental unknown to describe how these individuals will do in the competition. So typically, the equation you will write is that the change in the number of individuals, just like the dts and the dtp before, but now I write it as a PDE because you have two variables, is a Lotka-Volterra term, which means that there is a growth rate, the number of individuals which are born or which die is proportional to the number of individuals present multiplied by this growth and death rate. And this depends on the environment. And the idea of Darwin, which you have to put in the model, is that a newborn of type X can come from a mother of a type Y with a mutation rate from Y to X, which I describe here by parameter, by this kernel capital M. And all this depends on the environment. And the environment itself depends on the individual. So here I take a very simple rule where everybody is equal for the environment and the food is shared by everybody. So the only difference between individuals is how they die or multiply in this environment. Okay, so this is typically the equation which is now written as a PDE because it's more an integral equation than a partial differential equation, but the tools are more or less the same. What is surprising is that if you put these equations on a computer, that's what you will get. So here you get a solution of the equations. This is the trait, this is time. What you see is what is called selection by Darwin. So you have a selection, which means that only a single trait can survive. And after some time, a single trait is not good enough. And then the population will split in two kinds of species. And further, there will be 4 species. And the competition will make that the pressure will make that one of them disappears. And at the end, you have only 3 species. So this is very close to what Darwin wrote in his book. And the drawing that is in the book of Darwin, which I think is the first one where you see a graph like that to represent the tree of life. And you recover that. Here on the left, on the right, you have a stochastic Monte Carlo simulation of the same phenomena. So each time you describe these continuous models, of course you ask the question, but is there a more precise description in terms of individuals? Just like when you go from particles to the kinetic or the Navier-Stokes equation, you depart from particles. Here you can do that with a finite number of individuals. You look at the interaction of this individual with the environment, and if you if you describe mutations, birth and death correctly, you can fit the two models perfectly. This is what we did here. The mathematical, why all this is interesting in terms of mathematics? So the reason of that is, of course, that these equations have a very regularizing effect, which means that solution should be smooth. And the reason why you observe this concentration, which makes that your solution is really like a delta mass, like Dirac masses, comes by the fact that you have small parameters in the model. So typically the mutations are rare. Most of the reproduction is with the same trait, and mutations are rare. So you have to introduce these small parameters and these open questions, which are not only how to compute when you have these small parameters, but also how you understand what happens in the limit, and can you describe these dynamics now, not by the initial model, which is true at a certain scale, but at a new scale, just like you do Navier-Stokes from particles or from kinetic. So this is the first example that I see where you have a principle, which is the Darwin principle of mutations, and where you see some biology that everybody knows. But this is not the first partial differential equation which was written for biology. The first example of equation goes back to Kermack and McKendrick, and they try to improve the famous susceptible infected model, so SI model, which describe how an epidemic will propagate. So if so this model is just a number of susceptible, which people who did not get the infection will get infected because they meet an infected individual, and this infected individual will increase the number of individuals which are infected. And of course, there are death rates and the birth rate here. So when you are born, you are supposed to be susceptible. And sometimes you recover. So the B is a parameter for recovery. So infected people, after a certain time, it's a time scale, you become back susceptible. You lose your immunity. So this is an equation. These are ordinary differential equations, which are quite old. If you look at this Mémoire de l'Académie Royale des Sciences, so the Royal Academy of Science, before the French Revolution, you see that Daniel Bernoulli more or less was writing this. So Bernoulli, in this text, which is amazing, computes how many lives you would save in Paris by what they call at that time inoculation, vaccination. And to do that, he writes in the language of mathematics at that time, more or less this equation. This is a very nice equation also to study in calculus, because there are many properties which you can see on that, how you can use the Cauchy-Lipschitz theorem. So it's very usual to study that and to study the solutions, prove that the solutions are global and they converge to a unique steady state. So this is what you find in textbooks in mathematical biology. What is very interesting is that if you force the coefficients here, and especially the infection rate to be periodic, with a period of 1 year, because maybe it's not true in Hong Kong, but in Paris you get flu only during the winter. So this parameter is periodic, of period 1 year, and you see that this becomes chaotic. And when you compute the solution of that, you can fit with measurements which show that the flu is very unpredictable because the system is chaotic. So what Kermack and McKendrick decided that this model is not good enough. They wanted to describe the situation of disease in India, and it was not possible to fit. So what they proposed is a PDE, and what is interesting is that all the PDEs coming from physics which are described are always PDEs which describe a quantity, let's say temperature, depending on time at position x. If you get Boltzmann, you also say with velocity v. Here you can find partial differential equations where the parameter has nothing to do with space and time. Here, the parameter will be the age after infection. And so you count the number of infected people at time t with the age a after infection. And what simply Kermack and McKendrick proposed is that the number of encounters which create infections depends on the age in the epidemics or when after infection, and not only on the total number, so that the level of infection you get, if you want, is important. So now you have models like that. So you see that you have an equation which is a really partial differential equation, very simple because it's just a transport equation. But you see that now you describe an object which really depends on a continuous parameter, which is the time after epidemics, and which is given by this nonlinear equation. So again, I don't want to enter the details, but the mathematics behind that is quite interesting. These operators are not symmetric. They have a positivity principle because you describe density, it's better. So they are called the state structures. You have many of them, very different. And you have tools, just like the entropy tools. Here we are called the generalized relative entropy tools, which tells you what happens for a linear equation. It's also true, by the way, that this inequality is true for the model presented of Kermack-McKendrick. And beyond that, you have methods like Dublin's method. You have a question of spatial propagation, traveling waves, which are very interesting beyond that. You have question of networks, because nowadays everybody travels from Paris to Hong Kong, and you get a network of this kind of system which describe infections. So here you have an example of a simulation, which is the same as I presented before, but now it's a complete network, which is a computation by these people, where they included in the model all the big cities in the world, from south or north hemispheres. And what you can get are global pictures of the epidemics. So an example of calculation people did here, which is striking, is that usually when you ask the question, is the facility we have now how easy it is to travel from one continent to another one and from one hemisphere to another one, is it something which makes that epidemics are much more dangerous than before? And when you hear at the last 20 years where you had so many epidemics which are frightening humanity, you would think so. In fact, the conclusion is the contrary. Because all the travels around the world, any small mutation in a virus will spread everywhere. And everybody on Earth will, at some point, will be exposed, maybe not directly, but maybe indirectly, by this epidemic, by this mutation. And so you never have, in some sense, it could help to avoid, to be susceptible to big mutations. So everybody has a mutation, has a level of immunity which evolved together globally on Earth. So the new idea that I have seen on using this kind of models. A third subject where equations are well written are neuroscience. So in neuroscience, you describe electric potentials, which is the potential across the membrane of a cell. And you do that using the fact that along the axons, the dendrites of a cell, you have what are called ionic channels. And these ionic channels allow ions to enter or to leave the cell. And this regulates the transmembrane potential, the action potential V of t, and creates a polarization of the cells. This is more or less electricity. So the equations which describe that have been written quite early in the 50s, and Hodgkin and Huxley won a Nobel Prize for that. There have been many other models which have been proposed, Maurice Lécart, Michel Schaeffer, Fils-Zunaguma equations, which more or less describe all of them the action potential of a neuron. So again, the beginning is simply ordinary differential equations for each neuron, which I call for a neuron V. You get a system like that, which is quite big, where here you refer to all the ionic channels. So you have many ionic channels because you have many ions. So it can be potassium, sodium, whatever. You have all these ions in your body, which are regulated by this opening and closing of these ionic channels. So this GI refers to the gating, to the opening of this ion I. So usually people in this field, they use to something like 3 channels. These models are always very complicated. As this one, it's difficult to imagine what will be the structure of solutions departing from that. What I would like to insist on is this capital I of t, which are inputs, because these neurons are connected to other neurons. So they got inputs, and in this language, if I had the correct physical quantities, normalizations, this could be a current. All these models, whatever they do, they're interesting because they do always the same thing. So what you observe on all this equation is that the solution is made, if you depart far close to an equilibrium, is always is always formed by a very long escape from the equilibrium, which is called the spike, which is very narrow, and then you go back below the equilibrium, which is called hyperpolarization, and then you go back to equilibrium. So all these models, they're interesting because they do that, and this is what is observed on the neurons. And depending on the current, you can get just this relaxation. And if you put a current, what you get is that when you reach the equilibrium, the current will push you out of the equilibrium and create this long escape from the equilibrium and back to the hyperpolarization and so on. And then you get periodic solutions. So all this is not at all easy to explain on these equations. Why do they do that? So one direction has been taken by Fils-Zunaguma to simplify the model to a system of 2 equations where you can analyze with standard tools of a dynamical system. There are other ways to do that, and the physicists prefer what is called integrate and fire. So integrate and fire is a little bit different. It forgets about all the complexity of ion channels in the first glance. Afterwards, you can input them. You can put them back in the model if you want. But at the beginning, you say simply that the potential has tendency to go to rest, and V equals 0 is taken as the rest potential. You have a current I of t, which comes on the top of it, and you have a noise. And of course, when you want to look at the big networks of neurons, which is the final goal of all this, then what you need is, of course, to take into account that all these neurons will send information, and not all of the information will be processed correctly, so there is a noise behind which you can put. So the idea of integrate and fire is to forget about the spike, and so the spike, which is very narrow, we don't want to compute it. It's too complicated. It will be too time consuming to do that. What we do is when you reach a potential, which is a firing potential, rather than a spike, you go back to hyperpolarization. So you go back to a firing potential, which is below. So you introduce artificial discontinuities, which make that when you reach this firing potential, you are reset here to a new value of a potential which is below. So the reset is below. So this is, in some sense, describe what you see, where you have seen before, except you don't describe the spike. So you don't describe all these dynamics here, which is very narrow, you go directly from there to that, and then you describe this relaxation. And of course, if you do it here, it may be better. You see that you increase, and then you have a discontinuity. When you reach this potential, you go back to this potential. So this is much simpler than the equations I presented before. These are the ideas which were introduced by someone which is maybe not so well known, which is Louis Lapicque in the beginning of the 19th century. So Louis Lapicque is not very well known, but his brother is well known. Charles Lapicque was a famous painter who was a part of this idea of using colors in the beginning of the century. And this is not a picture. This is not a picture. This is a painting. So what you observe with these models proposed by Lapicque is exactly the same thing as with noise as you saw before. So you have a slow dynamics. You have this spike which are not described. So I put the spikes artificially on this drawing to see the spikes, but they're not described. When you reach the potential 1, which is the firing potential, you go back to the reset potential. You continue your dynamics, which is here a stochastic dynamics, until you reach another firing potential v equal 1. You make another discontinuity and so on. So physicists, because they wanted to have simpler models to work about big networks, they use this kind of descriptions. So here you have a list of names of those who have been doing that, and they try to understand if this can be fit to experiments. And this is an example of comparison where you have in black measurements on a neuron, and then on blue different form of the model, because you can change parameters or you can change the nonlinearities in the model just to see which one are the best adapted to each situation. And so they describe how you can go now from a single neuron to a network of neurons. And so the way to do that is to take capital N equations like that, where each neuron each neuron I will have a dynamics described by certain, let's say, relaxation with a noise, and in the middle you have a current. And the current is done by all the neurons which send a spike to the neuron I. So you have all the sum of all the neurons. Whenever they spike at a certain time, and these certain times are discontinuities, these are the spikes I saw before. Now we consider they are discontinuities, so you have direct masses at, depending on the neuron J and the spiking time K. And here you get a term, you have to renormalize, of course. If you have many neurons, you have to renormalize to get a finite number. And each time you reach the firing potential, you go back to the reset potential. So you introduce these discontinuities, which are exactly the spiking time you see here. At each spike, you create a direct mass, which creates a little bit of current. So what physicists knew, which is now proved by mathematicians, is that if you take a large assemblies of such neurons, capital N tends to infinity, you can describe the probability to find a neuron at a potential V. So you go from ODEs to partial differential equation, but now this is more or less a Kolmogorov rules, or Ito rules for stochastic ODEs. So you describe now the probability to have a neuron at a potential V, and here you get the drift which comes from the dynamics. This is the noise. And here you have all the dynamics, which is interesting, which makes that this model is not a classical Fokker-Planck equation, which is that all neurons which have been firing, they are at the potential VR. So you have a direct mass, you have a source of neurons with a potential VR, which is on the right. And if you want to compute how many neurons are like that, you do it from the boundary condition. So at VF you have no neurons, because each neuron which arrives at the potential VF will fire, so we'll go back to VR, so it disappears. So in fact, there is no neuron at VF. And then you have this flux of neuron, where the derivative gives you the flux, and the flux of neuron is exactly what you put here. So this is, you can check that this is describes well a probability. You have positivity and integral 1. You have introduced here the parameter B, which is a connectivity, which is connected to this parameter beta, which you put here. You can speak of excitatory neurons if B is positive, of inhibitory neurons if B is negative. So if B is positive, this creates a positive drift in the potential. You increase the potential, you go faster to the firing potential. So you increase the number of firing neurons. If B is negative, you create a drift in the negative values of V, so you will avoid firing of neurons. So what we discovered, which is what was a surprise for a physical model, is that the solutions of this equation do not always exist. And here is what happens if you look at the dynamics. So what you create first a kink, which is a Dirac mass in the right-hand side, so this is physical. And here you have the normal derivative, which gives you the number of firing neurons, and you see that it increases. It decreases continuously until the slope becomes infinite, which means that a certain number of neurons have been firing together. So if you look now, at the number of neurons which are firing at the time t, you see that at the beginning it's increasing, and then it blows up in finite time. So in some sense, the model doesn't make sense. So at the beginning, we thought it was an artifact of the model which was not good and was not physical. In fact, speaking with physicists, they explain us that's exactly what you want to describe. Because what we consider as the blow-up, what we say the solution stops being existing, is not that. It's simply that a part of the network synchronizes. And what you think to be an infinite number of neurons which blow up means simply a part of the network synchronizes and begin to fire all together. So if you want to regularize a little bit the system, so the system clearly misses something to describe a smooth function. So you can do it in different ways. You can put refractory neurons, you can put randomness in the firing rate. What you obtain at that time is that the solution, so here I've increased, I've put a random firing potential, so it changes randomly, so you can have neurons with a potential larger than VF. You have always the kink, which is the Dirac mass, which is normal, and of course, you create a big slope, but the system now has a smooth solution, and when the slope is large enough, there is a complete set of neurons which will discharge, and the solutions become periodic. So this is what you see here. You have, after some time, so you have a solution which is periodic and which seems to be attractive. It's an open question to prove mathematically that this object exists and that they're attractive. They're beginning to have interesting results in this direction, by the way, very recent ones. Okay, let's go on in biology and now consider another question in biology, which is have to do with bacteria. So bacterial motion poses a very interesting question. Bacteria are very simple organisms. They are individual cells which are very, very old on Earth. They are the first living species which arrived on Earth billions of years ago, and they communicate only by sending chemical signals outside and measuring the external chemical signals. So in some sense, the communication method is very, very, very loose. Nevertheless, when biologists cultivate these kinds of bacteria in a petri dish, that's what they observe. They observe that the colony of bacteria, here you have millions of bacteria because they have been dividing during 24 hours in good conditions. They create shapes which are like that, which means that collectively bacteria find an organization which is better to get the food. The good food is of course outside because the inoculation is in the center, so you have the food here has been completely consumed. And those cells will communicate in such a way that collectively they create this kind of shapes, which of course is better. If you want to find the good food, it's better to send a small colony than to go globally all together to the boundary. So this is what they think is the reason of this organization. So you can describe you can use now mathematical models to explain that. And one of them is based on a work by Mimura in Japan and reproduce perfectly well this kind of pictures. So here what you see are different things. Here you see the nutrient which is consumed by the cells. So that's the nutrient which is initially on the dish, which is used to do. And here you see the cells which are dividing. And here you see the total number of cells. And after a while, cells are too much packed and they don't move. That's the reason why after some time they stay there. So here there are frozen cells which do not move. These are cells which are moving and dividing. So you have explanations like that which are given by mathematical models. You have another example of a simple organization of cells. So we are speaking now of another bacteria. And what you observe in that example is much simpler because not 2D, it's only 1D. And what you observe is simply a wave which is propagating. So what you observe in this experiment is that all the cells, they will move together at a certain speed. So you see different times here. You see that the speed is constant. And if you look at the shape of the density of cells in this signal, this density is more or less constant. So these are experimental data given to us by a group in the Institut Curie in France, in Paris. So the movie which shows the experiment is this one. So you see that you initiate a wave here, the wave propagates, and when you measure, you get okay. Here the propagation rate is contrary to is the opposite of what you see here, but it's the same phenomena. You see that this profile is constant, and you see that the speed is constant. How can you explain again that simple? So that simple living objects like bacteria will do that. So this is an old subject since Adler's experiment, which show that. And again, there are names associated to equations to describe that. And the name here has the name of Keller and Segel. It's one of the most studied mathematical problems in biology. It turns out that there is no very clean explanation of the reason why you do that, and especially because we know that these cells are chemotactic, so they have tendency to send a signal which attract the other bacteria. So if you want to understand that, it was introduced in the 80s, the idea that you should look again at the individual cells, not at the population of cells. So you don't look at the million of cells which are in the density which I have shown before. You look at each individual cells. And in the 80s, biologists were able to measure and visualize individual cells. And so what they understood is that cells are moving by what is called run and tumble, which means that rather than Boolean motion, what they do is simply that they take a direction, change direction, move a little bit, and change direction again. So if you want to describe that, what you have to do is to go back to the ideas of Boltzmann and write the density of cells which at a position t have a velocity at the time t, a position x, have a velocity psi. And what you have to say is that these cells are running with a certain velocity psi, and they tumble. They have a tumbling rate, which is depending on the chemical environment, C or S. So here I have put a chemical which is a chemotactic signal, which attracts cells together, which is emitted by cells, and I've put a substrate, a food, S. All this will regulate the way cells are moving. If you do that, so what we propose with Xian Wang is to understand this kernel, and what is known for this kernel is that it's very stiff. So this kernel not only is very stiff, but it depends on the variation of the food along the path, and or the chemoattractant, or any chemical signal that it can sense. So they measure along their path, which has a velocity which are called psi prime. They measure the variation. If they like it, they will not move. K will be small. There will be no tumbling. If this is small, okay. So if this is the positive, the solution, the chemoattractant increases. The cells they like it, and K epsilon will be small. If this is negative, they don't like that direction, and K epsilon will be large to turn and to go to find a new direction. And this is done in a very stiff way. This is measured by experimental devices also. So you can take this parameter, just like we took the mean free path for the Boltzmann equation. You can take this parameter in the, as a rescaling parameter to say that you scale now, you look at the population rather than at individuals. And when you do that, you find out a variation, which is called the flux emitted Kähler-Segal, which is a variation of the Kähler-Segal limit equation, in which you get a Fokker-Planck equation where the velocity u depends on the chemical, so the quantity c, with a saturation term phi. And the advantage, so this model, which you can only invent because it comes from a microscopic equation, has a property that you have very robust traveling pulses, which you can fit compared to experiments. So this pink curve is a solution of that, and the blue curve is the experimental measurements. And you can explain exactly why you understand everything. You can explain exactly why you get this shape and what is the role of all the parameters. In this kind of experiments, biologists knows more or less, that's an exception, but they know more or less all the parameters. So it's more or less like physics. You know exactly what are the tumbling rate at rest with a certain level of chemoattractant and so on. The only thing they don't know is the concentration of chemicals outside of the cells. So this is another example where you have a population scale, which is a Kähler-Segal equation, or the flux emitted Kähler-Segal equation. You have a kinetic equation. And what is interesting is that nowadays you have also a molecular scale. And now you want to explain the individual scale, the motion of at the individual scale, by the internal molecular pathways. And this is where mathematics is now. You have a new parameter, which is the chemical concentration inside the cells. And cells are now described a big number of quantities. And you can also play rescaling to understand all that. I would like to conclude with an example which doesn't really come from biology, which comes more from medicine, but which has to do also with fundamental questions of how cells are organized, which is the question of to describe living tissues. And these questions of describing living tissues arise in several areas of biology and medicine. One of them is developmental biology, when you want to understand how a body will develop. And in medicine, you want to understand the tumor growth, for example, or cancer. So these are examples of experiments where you see, so typical tumor in a solid tumor is done by what is called a proliferating rim, where you have here cells which are proliferating, and here a necrotic core where cells are dead. Here another one, this is a bone cancer. And here you have numerical solutions which are here based on individual cell modeling, and here a continuous model. So this subject of living tissue is a subject which is a current subject in biology. You cannot say that everybody agrees on the models. If you take 10 years ago, people would have proposed mathematical models which are quite different of what is done today. So this is really biology and medicine of today which is behind, and various sciences are involved in that. So you can find people from mechanics which consider that as a fluid. I mean, in some sense, the living tissue is at certain scale a fluid. You have mathematicians who try to understand the equations behind. Of course, you have biologists and medical doctors who also want to understand that. So the understanding I take from mechanics is the following. You have a number of cells at a position x. They move with a certain velocity v, and this is due to a pressure p. So these are really ideas from fluid mechanics which are used here. And the main difference between a tire and a living tissue is that in a living tissue, not only cells are moving, but they divide and they die. And all the dynamics will be here. So the image you can have is when you have a tumor or a tumor which is growing, cells are uptaking nutrients, they are growing. They are dividing, and because they divide, they push the other cells. So you have this phenomena that in the middle, cells are dividing and pushing, but just by pressure, the rest of the tissue. So this is what is written here. You have a Darcy law, which tells you that cells are moving according to this pressure, and there is a friction, and the friction is due simply to the fact that a tissue is also an extracellular matrix. So you have this matrix, which is made of collagen, of fibers, of all kinds of fibers, and cells have a friction against this extracellular matrix, which is just like in a fluid in a porous media where you have friction on the boundary. So in a compressible view, you complete that by a constitutive law, which is, of course, one of the difficulties of the model, of what is a constitutive law of a living tissue. But you can write equations. And the idea, which is a new idea from 10 to 20 years ago, is that the division rate is controlled not by the number of cells, but by the pressure. And this idea, up to my knowledge, goes back to Ellen Byrne and Dirk Drasdo in a paper which was based on numerical simulation. And so you get a new type of equation, which looks like the porous medium equation, but which asks many, many mathematical questions which are new, especially because you have a pressure which is called the homeostatic pressure, where this quantity will become negative. If you go above the homeostatic pressure, then cells will become to die, and this has been measured experimentally. Okay, do it like that. It will be simpler. So these models are also connected to fluid boundary problems, and people who really compute with this, they don't use the formalism I showed with the compressible equations. What they do is consider that that the tumor is given by a certain geometrical object, and that the cell density here is of tumor cells is big, or is 1, is saturated, and is 0 outside. So that the tumor is a well-identified object, geometrical object, that you can compute a pressure just by computing the solution of the elliptic equation inside the domain, saying that the pressure is 0 outside. 0 is the pressure of the healthy tissue. It's taken as the reference pressure. And you compute that, which is, of course, much easier, because now you just have to measure, to compute what is the boundary here. And the boundary, you say, just moving with the velocity grad p. So at each time, you have to compute the velocity, which is given by a simple elliptic equation, and you can compute then the deformation of the tumor. So I was very surprised that you have two schools in mathematics: those which consider the porous medium equation, the compressible models, and those which consider more this free boundary problem, this geometrical motion. And in fact, we understood with Juan Vasquez and Fernando Quiroz that they are very well connected. And simply, if you take the compressible model with a very stiff pressure, so you say that if cells are far away, the pressure is 0, or the pressure is 0. And as soon as they are close enough, there are very little place to compress, because each cell individually is an incompressible media. And so if you take this limit of a very stiff pressure, what you can prove is that the compressible models give you the free boundary problem. So this is connected to what in fluid mechanics to what is called the L-Eschaut flow, and there are many mathematical questions around this limit in these situations and more complicated situations. Just I want to like to show comparison to show that all this is not completely a mathematical view. Here you have an example of a numerical simulation where you see more or less this free boundary where the cell density is 1 and 0 outside, and a pressure which is pushing the cells. And here is an experiment where you have here the cell density, which is more or less constant up to statistical errors, and a free boundary which is very stiff here. So you can compare again the models with the experiments. I'll show you. Okay, continue maybe with more elaborated model, but it's called, of course, a single equation. You understand is not enough to describe a tissue. So in fact, you have to include more. It means after this basic brick, you have to include more physics or more biology. One of them is to say that nutrients arrive. I mean, nutrients are important. They are released by the vasculature and diffused. Nutrients means, for example, oxygen, which is diffused in the body. And so you can put that. If you do that, what you see is that now, which you cannot get with the other model, is that now a tumor will grow with cells which do not have access to the nutrients in the middle. So the nutrient comes from the vasculature, which is outside, is diffused. So in the middle, there is no nutrient left. Oxygen is consumed by these cells which are dividing. And what you see in the middle is a necrotic core that you have seen on real tumors. So you can recover that if you put now a nutrient. What is interesting is associated to that, you can have instabilities, that the tumor doesn't remain completely round. You can also say that cells do not react all the same they have not the same elastic response to the pressure. And if you do that, you can find also instabilities, which you can also see in experiments. So if you put enough of this biology, so you put that there is nutrients, so you need a vasculature to bring the nutrients, which I did not describe. All cells are not the same. There are quiescent cells, there are necrotic cells, and there are FE cells, of course, so you have to put many of them. If you have a model which is good enough, you can do these computations, which are accurate, which are computation on real images of patients, which is done by a group in the city of Bordeaux, where they try to predict the growth of tumors in patients which arrive in the hospital. So these are 3D computations on real data. And by the way, the computation was so convincing to medical doctors that these people created a startup company which is doing that in the hospital. Okay, so I will conclude now at this stage. So I tried to explain that biology is full of partial differential equations. You can find them in ecology if you want to describe Darwinian evolution, epidemic propagation, neuroscience, bacterial population organization, and tissue growth. These are examples. There are many others which I took to have a certain representation of biology. The common thing is that there are many scales. There are always small parameters and there are many scales, so asymptotic problems are very important here. And the two ideas that I would like to underline is that we are in a situation that in some situations now you can really compare experiments with models. We are in situations where the models have been fit with experiments, and that there are concrete applications to all this. I would like also to underline the difficulty, especially in medical science, which is behind this computation I showed at the end, which is unlike physics, where parameters are very well known and are are known for decades. In biology, most of the parameters are not known. They are extremely variable. They are not completely fixed. That depends on many parameters on the environment of individuals. And so the question now in this model is not to compute the model with a single set of parameters, which would be the set of a patient. It's to compute the solutions with parameters which are distributed according to certain laws, and which ask new questions in PDEs, where we have very little questions. Means these 3D computations are taking more or less all the computer time of a computer like we have in my laboratory. And so you want to run it not only for a certain set of parameters, but for a distributed set of parameters. So how do you use that? Can you do that in an effective way? I would like to thank my collaborators on that, which are here, and I thank you for your attention.
I think we are open to any questions.
Yeah. When you showed the examples of cities regarding the flu.
Yes.
Yeah. For some cities, it's every year it's the same. For some others, it's quite different. So how does it come from the equation? How do you know which time you would?
There is no analysis of this kind of things. Absolutely no analysis. It's just numerical simulations, which are based on real data on real city. But this depends very much of the latitude of the cities. If when you have seasons which have very big variations, then you have also big variation in the flu.
But you don't see this in the equation.
No, absolutely no. It's a big system of equations, and so this is very interesting. At this stage, what they know is how many people will travel from New York to Paris or to Hong Kong, and they put these numbers in the model to obtain that. So that's really complete numerical simulations. What I think mathematically is interesting is that for a single equation, if you force it periodically, already it becomes chaotic. A very surprising fact on this very simple system.
Thank you very much for your very nice talk. I have a general question. So, in your talk, you present many simple models describing different biological phenomena. When I say simple, by no means easy. Okay? Mathematically model is simple. But on the other hand, there are large number of people working in mathematical biology. They propose very fancy and complicated mathematical models by taking into account many detailed factors of the in biology, but they only can do very minimal mathematics, by showing numerical simulations and so on and so forth. Basically, there are two types of the mathematical biology. Like, what do you do? Okay, do simple mathematical model, but we can do many beautiful mathematical analysis. On the other hand, they can propose complicated mathematics. So, do you have any suggestions for mathematical biology?
What you say is also true for models of physics. Yeah. If you look at engineers who compute really rarified flow in a satellite, they will not use the Boltzmann equation of mathematicians with monoatomic gas and so on. They will use the degree of freedom of molecules. They will put possibly quantum mechanics because molecules are vibrating. And so when you look at how engineers use the Boltzmann equation, you could say this is very complicated, I cannot understand anything. It's the same thing. But if you look at the simple monoatomic gases, then you understand many aspects of the equation. So it's also true, I think, between physics and engineering. If you look at Navier-Stokes equations, the equations I wrote on Navier-Stokes, which are those that mathematicians are using, is not what you will see in an aerodynamic laboratory where many parameters have to be included and boundary conditions and so on. So I think it's also, so in biology it becomes much more important because the complexity is much higher. So more or less in engineering, you build the object you want to build. In biology, you have to face objects which come from nature and from the evolution. So it's much bigger complexity. But it's the phenomenon itself, you already find it before in physics. And everybody agrees that physics is useful for engineers. So in the same way, I would say mathematical biology is useful for these complex systems you are speaking of.
I'm wondering whether you're optimistic about deep learning and whether it could, if you train a network, supplying the input and output, maybe the patterns, maybe in the end it will describe something that's similar to a differential equation. I wonder how you, is that a possible way to go? But that, of course, would mean that mathematicians will have less contribution to make, but I wonder what you think about that.
Okay, there is a whole branch of neuroscience which I have not time to speak about, which is about how neural networks are formed, but learning in neural networks, how the connectivity in networks are performed. So here I consider completely homogeneous networks, which are simple. Everybody is connected to everybody. But the next step is, of course, to say that there are specific connections, that these connections are learned by the inputs, and this is a branch of the field of neuroscience. The main difference with deep learning is that in deep learning you decided of very simple rules and you use them just as a way to manipulate that data. But there are many common points behind that. But again, would you want to do something which is simple, where you understand what happens and how this connection will be done, or how you use it in practice and with real data? So always the same question. But I think the origin of deep learning are the models of neural networks. Mm-hmm.
Okay, last question.
Thanks for your great talk. So I'm wondering if we want to model the infectious disease among like a spatial area. Nowadays, to make it more practical, we need to incorporate geographic information system.
Yeah.
But in reality, the system or each particle move doesn't just like a diffusion process or doesn't like a wave. People can travel through the flight or the train and or the ferry or drive. So it's not just like have a close contact through the neighborhood. So how in this modern world, so is there a simple model that we can model all those kind of connection at the same time?
Yeah. So that's very very simple. You for each location you generate a system like that, and you connect all of these elements of the network by source terms in the network in each equation. So, for example, if you look at the susceptible, will encounter an infected person. In the infected person, you have to count the population which is infected, but also those which come from outside which are infected. And this you can do if you know the number of people flying from New York to Paris. You can know the proportion of infected people which will bring the disease in Paris or from north to south hemisphere. So you can find you can have access to the numbers and put that in the models. But then you get discrete models, which are networks or discrete networks which are connected and with real numbers.
So we can't use PD
anymore. No, these are not PDs. They are really discrete networks. Yes, just like at the beginning for neuroscience, you take but for epidemics, more or less. Okay, when you look at the size of a city, you want to understand in the city how the epidemics will propagate. Then more or less it's continuous, because then you will see that many people travel in all directions, so you have a continuous aspect. If you look at, so in London they do, in England they do that very much in all the cities, to understand how the epidemics will where it will arrive and where it will propagate, and this is more or less continuous. But if you look at these examples of the global picture, it's discrete.
Thank you.
Okay, I think we may like to give thanks to our speaker today, and I would like to present a souvenir from our university. Thank you very much for your talk. It's very interesting. Okay.
Thank you.